Hello, good afternoon. Last time we have seen several questions based on dynamic programming formulation. So this was a question based on longest common subsequence. So the correct answer for this question was that the elements of the computational matrix in the computation of longest common subsequence, it can be computed in a row major order or in a column major order. Okay, so the correct option for this question was this option number 2. The values of Lij. Lij is nothing but that computational matrix may be computed in the row major order or column major order, okay, of Lmn, where this m is the number of elements in the first string and n is the number of element in the second string. Okay, then this is the next question. Subsequence of a given sequence is just given sequence with some elements left out. So we are given this sequence, two sequences xm and yn of length m and n respectively, with the indices starting from 0. Okay, so 0 to m minus 1 and 0 to n minus 1. These are the range for the x and y. So we wish to compute the length of the longest common subsequence as Lmn. So this Lmn is nothing but the length of the longest common subsequence by considering m characters of first string and n characters of second string, where an incomplete recursion definition is given this in the form of expression 1 and expression 2. So Lij is equal to 0 if I is equal to 0 or j is equal to 0, means if we are computing the first row or first column of the computational matrix, then it is 0. And as we have already seen that in the initialization part of the algorithm, that first row and first column is initialized to 0. Then this second one is expression 1. When we match the character, then what we saw actually, when the characters are matched, then we will take the diagonal entry and we will make it +1. So we will just take a recall of this. So this was the LCS algorithm. Here we can see that if the characters are matched, here the ith character of first string is matched with the jth character of second string, then what we will do, we will take the diagonal element that Cij is equal to Ci minus 1 j minus 1. This is the diagonal entry and +1. Okay. So just come back to this question once again. So this expression will be look like this: L of I minus 1 j minus 1 plus 1. Okay, when this character is matched. And if it is expression 2, when it is a mismatch, then what we will do, we will take the maximum of leftward entry or rightward entry. Okay, so here some questions are options are given. Which one of the following options is correct? So any one option is correct here. So we will two options are corresponding to expression 1 and two options are corresponding to expression 2. Okay, so first of all we will see expression 1. So expression 1 will be suppose something I minus 1 j minus 1 plus 1. So here we can see I minus 1 j, this is wrong. This expression 1, once again it is I j minus 1, it is also wrong. Then we will see expression 2, it is nothing but the max of I minus 1 j. And what is I minus 1 j? I minus 1 j means we are talking about the previous row. Okay, if we are at ith row, then I minus 1 row is nothing but the previous row, and j is remain same. So j is nothing but the column. Okay, and this is nothing but I and j minus 1. So j minus 1 is the previous column. Okay, so this is this is upward and this is leftward. So we are taking leftward and upward entries, and we are considering the maximum of those two entries, and we will decide this for the expression 2. So option C is the correct option. Just have a look on option this expression fourth option, option D. What it is saying? It is expression 2 is equal to max of Li minus 1 j minus 1 comma Lij. So this is wrong actually, because Lij that we are computing itself. So how can we use this Lij in the computation of expression 2? So the correct option here is option C. Okay, now see the next problem in the series of dynamic programming formulation. The first The next problem is known as binary knapsack problem. We had already seen the fractional knapsack problem. What was fractional knapsack? Fractional knapsack, when some elements are given with some weight and profit associated with each of the object. And what was the main difference between a fractional knapsack and binary knapsack? The main difference was that in fractional knapsack you can include a fraction of the object, but in binary knapsack it is not the case. If you want to include the object, then you should have included completely, otherwise you cannot include this. Okay, so the fractional inclusion is not allowed in case of binary knapsack. So see the problem statement, and after that we will see what is going on here. So binary knapsack or 0-1 knapsack problem is also a classic example that can be solved using dynamic programming. The problem statement is this: given n objects, each and every object is associated with unique weight and profit, and one knapsack capacity is given. Knapsack is nothing but a bag. The capacity of this bag is C. Then what we have to do? We have to select some of the object within the capacity limit of knapsack so that the profit should be maximized. But what is the restriction? Either the xi should be 1 or xi should be 0. It cannot be something between 0 and 1. Okay. Now see more formally the problem definition. PK is nothing but the profit associated with the kth object, and WK is the weight associated with the kth object. Okay, and K is ranging between 1 to n because n objects are there in consideration, and xk is either set xk is set to either 0 or 1. So xi is nothing but inclusion of first object decision. Okay, x2 is nothing but decision on the inclusion of second object. X3 is the decision of inclusion of third object, and so on. Okay, and it can be either 0 or 1. And if the 0 if case object is not included, otherwise 1. Now this is the main formulation. Let Tij is nothing but the maximum profit by considering the first ith object, and the considered capacity is J. What is the maximum capacity? The maximum knapsack capacity of this problem is C. Okay. So here we are taking two parameters. I indicate the first I object that is considered, and J indicate the considered knapsack capacity. So what we are interested in? We are interested finally in T and C. What is N? N is the number of objects, total number of objects. Okay, and C is the total capacity that we are interested in. Okay, so we start the computation from this, and the final entry that will be computed in the computational matrix is this T and C. Now I'm repeating this once again. What is Tij? Tij is nothing but the maximum profit by considering first I objects with the considered capacity as J. And what is our aim? Our aim is to select some of the objects such that we can maximize the profit. So how the profit is computed? It is computed for all the objects. Pk multiplied by xk. Pk is nothing but the profit associated with kth object, and xk is the decision. It can be 0 or it can be 1. Okay, so if it is 1, then profit is included, and if xk is 0, then this profit is not included. Okay, so we want the maximize this expression subject to what is the condition or what is the constraint here for this particular problem. This is wk multiplied by xk. What is wk? Wk is nothing but the weight associated with the kth object, and it is multiplied with xk. So it should be less than or equal to c, because we cannot go beyond the knapsack capacity. And for a non-trivial solution of 0 by 1 knapsack, this binary knapsack is also known as the 0-1 knapsack problem. So for a non-trivial solution, this summation of all the weights of all the object, summation of weight of all the object should be greater than 0. Why it should be? Because if summation of weights of all the objects is less than c, then there is no need of solving this particular problem. We can include all the objects, okay, irrespective of any condition. Because if we include all the objects, then also it is less than the knapsack capacity. Okay, then we do not bother about this. So that will be considered as a trivial solution. But here, for a non-trivial solution, this should be the summation of weights of all the objects, they should be greater than c, so that we can have a decision on the object whether it should be included or it should not be included. Now we will have a look on the algorithm. Now see binary MSEC problem. So here we are taking three arguments. This is T that we are computing, T of ij, and the value, the dimension of this T will be n cross C, or more specifically we can say n plus 1 cross C plus 1. And the C is the capacity of the knapsack, and N is the total number of object in consideration. Okay, so the T is the profit matrix of size N plus 1 cross C plus 1. Here you can just notice that the size of this T is not N multiplied by C, it is N plus 1 cross C plus 1. Okay, so we will take the first row and first column. The element of this particular T matrix is initialized to 0. This is the initialization. For C is equal to 0 to C, it is ranging from 0 I. So what we are initializing here, we are initializing the first row to 0. Then it is ranging from 0 to n, and T of I0 is initialized to 0. It means that we are initializing the first column of this matrix to 0. Now here you can note that 0th row and 0th column have been initialized by 0. Now it is starting from 1 to n and 1 to C. Okay, so now the remaining matrix is computed. So see how it can be computed. First of all, when I is equal to 1, then which object I am considering? I am considering the first object. Okay, then I will check if weight of the ith object is less than or equal to C. Means the weight of that particular object is less than or equal to C, then only we will consider something. Otherwise, weight of that object is greater than C, and what we will do? We do not bother about this. Okay, we cannot include this anyway. So we just go in the else part, and Tij is assigned to Ti minus 1j. Okay, what is Ti minus 1j? Ti minus 1j is nothing but the maximum profit by considering first I minus 1th object, and the considered knapsack capacity is j. Why we are not considering ith object? Because here the ith object weight is greater than C. That's why we come in the else part. Okay, now see, if this condition is true, then we can have a chance that we can include this. Okay, now see here, the considered knapsack capacity is J is also changing. It is ranging from 1 to C. Suppose the knapsack capacity is 20, then this for loop is running from 1 to 20. The first time the value of J is 1, then the value of J is 2, then the value of J is 3. Okay, we will see one example also. And then if profit of ith object, if Pi is plus Ti minus 1, comma J minus Wi. What do you mean by J minus Wi? See, if considered knapsack capacity is J, suppose considered knapsack capacity for an example, just J is equal to 10. Okay, then J minus Wi. Suppose the ith object weight is 5. Okay, so J minus Wi is nothing but 5. Now what I am checking this by considering first I minus 1 object with the considered capacity J minus Wi. Okay, and if we include the current object in this, okay, first of all, J is reduced, Wi is deducted from J. Wi is nothing but weight of this particular object, so that we can check if this expression, entire expression, is greater than Ti minus 1 J, then only there is a chance of inclusion of this. Okay, so here considered knapsack capacity plays a very important role. Considered knapsack capacity is J, but what I am checking, J minus Wi. So J minus Wi is nothing but the scope of consideration of the ith object. Okay, so J minus Wi decide the inclusion of this this ith object or not, and profit Pi is nothing but profit associated with ith object. If this expression is greater than this, then Tij is updated to this expression. Otherwise, Tij will remain Ti minus 1j. What does it mean? It means that if we include ith object, then we are not getting something uh, better than the existing scenario. Okay. Now, when we have computed this, the entire T matrix, now we need to decide that which object have been included and which object have not been included. Now, just see in which statement we are deciding whether the ith object is included or not in this statement. Okay, if this condition is true, it means that we can include this particular object. Okay, so if Tij is equal to Ti minus 1j, it means that we are not including that particular object. Okay, and if Tij is not equal to Ti minus 1j, it means that that ith object is included. Okay, now see, in print bk, print binary knapsack, we are passing this t, n and c, and we are just printing which object is included or not. So I and j is initialized to n and c respectively. These are the some variable. N is the number of object and c is the considered capacity, while I is not equal to 0. So this is a loop. Now you will check, if t of ij is not equal to ti minus 1j, when you will get this, when this is Tij is updated, and in both of these remaining two cases, Tij is equal to Ti minus 1j, and here also Tij is equal to Ti minus 1j. But here in this statement, Tij is not equal to Ti minus 1j, it means that we are including that object. Okay, then you will check, if Tij is not equal to Ti minus 1j, then what we will do? Mark the ith object as in the knapsack, means include this item. Okay, now we have taken the decision on the ith object. Now I is reduced, I is equal to I minus 1. For example, suppose n is equal to 10, it means that 10 objects are there in consideration. Okay, so the initial value of I will become 10. Now you will check, if Tij is equal to Ti minus 1j, then we have take the decision on the 10th object. Okay, when we have taken the decision on the 10th object, then we will consider the 9th object. Okay, how can we get the 9th object? I is reduced by 1, I is equal to I minus 1. And what is j? J become j minus wi. What does it mean? See, that object, if that object is already included, then j should be reduced. Okay, j is nothing but the j is initialized to the knapsack capacity. Okay, now if object is included, then j should be updated, j is equal to j minus wi. Okay, it holds the remaining knapsack capacity. So j object variable j indicate the remaining knapsack capacity each and every time. Okay, and if this condition is not true, this if condition, if it is not true, it means that ith object is not at all included. If ith object is not at all included, then there is no scope of reducing the remaining knapsack capacity. Only the previous item is considered. So in this case, we just go in the else part, and I is equal to I minus 1. Only difference between if construct and else construct is that in if construct we are considering j is equal to j minus wi. Here we are not considering j is equal to j minus wi, because here the ith object is included, and if it is not included, then it will not going to affect the remaining knapsack capacity. Okay, and when will this condition will true, uh, we will go inside when I is not equal to 0. At some point of time, the I will become 0, then you come out of this loop. After that, we will see one example. Just let us consider the number of objects are 4, n is equal to 4. The knapsack capacity is 5. See here, when it is a 4 cross 5, then you will be constructing a matrix of size 5 cross 6. You will be constructing a matrix of 5 cross 6. So here you can see first row, second row, third row. Okay, so this is the matrix of 5 cross 6. So 4 objects are given. So each object is associated with a profit and with a weight. So first object profit is 3, second object profit is 7, third object profit is 2, fourth object profit is 9, and the weight is this 2, 3, 4, 5. These are the weights. Okay. Following table specifies the profit and weight of the kth object. Now what we will do, we will just see here. Here you can note that this is the first for loop, okay, which is running for I, means for the number of object. So here we can note that when first object is considered, then the knapsack capacity is considered knapsack capacity is increasing. So if we consider this particular cell, okay, then what is the considered knapsack capacity? Considered knapsack capacity is 1. Then if we consider this particular cell, then the considered knapsack capacity is 2. If we consider this particular cell, the considered knapsack capacity is 3, and so on. And in this entire row, how many objects are considered? Only first object is considered. Now see what is happening over here. If the first object is considered and The considered knapsack capacity is 1, but what is the weight associated with first object? Weight associated with first object is 2. Okay, so if considered knapsack capacity is 1 and weight associated is 2, then we cannot include this. If we cannot include this, then the associated profit will be 0 only. Now see, in the second case, the considered knapsack capacity is 2, but only one object is considered. So here we can note that if single object is considered and if we are increasing the capacity, considered capacity, then we are not increasing the profit. Okay, we are, because only single object is considered. However, when we are computing the second row, just come here. When we are constructing or when we are computing the second row, it means that how many objects are there in the consideration. It means that the first two objects are there in the consideration. Okay, see here, when first two objects are there in consideration, then first two objects, what is the total weight associated with the first two object? Weight associated with the first object is 2, weight associated for the second object is 3. So total weight associated with first two object is 5. Now here you can note that if we consider the considered knapsack capacity is 5, then only this is 10. What is this 10? 10 is nothing but the summation of profit associated with first object and summation and profit associated with the second object. So profit associated with the first object is 3, profit associated with the second object is 7. Okay, then 10 is there. Before this, considered knapsack capacity is 4. If considered knapsack capacity is 4, then what we will do? We will just can consider only single object. And which object is considered here? The second object is considered because profit associated with that particular object is larger as compared to the profit associated with the first object. Similarly, we will compute the entire thing, and the final profit associated will be this is the final entry that we are interested in. What is this entry? This entry is known as C and C. Okay, this N is 4 and this C is 5. Okay, so T and C is the final entry, and what is the total profit? Total profit is 10. Now I need to decide that which object I have included and which object I have not included. Okay, so for that we need to check this. First of all, we will see this. If ij is not equal to I minus 1j. Now here we can see ij is 10, I minus 1j is also 10. Okay, it means that we have not included the fifth object. Okay, thus I is reduced. Then this 10 is compared with this 10. It means that we have not included the fourth object. Okay, then I once again I is reduced. Then similarly we will check if Tij is less than I minus 1j. Here it means that third object is included. Okay, so third object is included, and similarly we will see this. So based on this algorithm, we will be deciding which object is included and which object has not been included. Okay, now see some problems based on this knapsack problem. The first question is that the subset sum problem is defined as follows. Given a set of n positive integers, a1, a2, an, and a positive integer w, is there a subset of S whose elements sum to w? Dynamic programming for solving the problem uses a two-dimensional Boolean array X with n rows and w plus 1 columns. Xij is equal with Xij, where I is ranging from 1 to n and j is ranging from 0 to w. Here we can see that this is nothing but the capacity which is ranging from 0 to c. And it is true if and only if there is a subset of this a1, a2, a3, and whose elements sum to j. So we have already seen this. Which of the following is valid for I is ranging from 2 to n and j is ranging from ai to h, w. So here xij is equal to xi minus 1 j v I j minus ai. See what is the characteristic equation here? You can note here. This is the characteristic equation, the maximum of this. It can be I minus 1j, it will remain there, and if it is not I minus 1j, then it is nothing but I minus 1, j minus p, j minus wi. So this is I minus 1 j, and it is common in all this I minus 1 j. V is nothing but the profit associated with this. So it is nothing but I minus 1 and j minus ai. Okay. So I minus 1 and j minus ai. Here we can also see that what is the difference between option 2 and option 4. Actually, these two options are same, and basically this is the answer. Xij is equal to xi minus 1 j and v of xi minus 1 j minus ai. Okay. Then the second question. The subset sum problem is defined as follows. Given a set of n positive integers and a positive integer w, where w is nothing but the capacity, is there a subset of S whose elements sum to W? Okay. Then a dynamic programming is for solving this question use a two-dimensional Boolean array X with n rows and W plus 1 columns. Okay, the same question is there. It is asking which is the final entry that we are interested in. So which entry of the array X is true? If true, implies that there is a subset whose element sum to W. Okay, so what is the final entry that we are interested in? This is nothing but the X and W. Okay, here in the algorithm that we have seen, it is nothing but T and C. In the algorithm, we have used a C notation or C variable for denoting the capacity. But here W is considered as a capacity. So correct option is option C. Okay, in this series, we will see another very important problem known as optimal binary search tree. So, as the name suggests, what is binary search tree? Binary search tree is a binary tree in which the left side is smaller as compared to root and right side is larger as compared to root. Okay, so this is known as optimal binary search tree. So some keys are associated with the binary search tree. So based on the searching probability of each and every key, we need to construct the binary search tree such that we want to reduce the number of comparison basically. Okay. Now see here we are having two example or we are having one example in which two keys can be demonstrated by these keys. So here we can see how many successful keys are there. So five keys are associated with this K1, K2, K3, K4, K5. What is the relationship? If you draw the in-order traversal of this, then you will get a sorted sequence K1, K2, K3, K4, and K5. Okay. So these are the searching probability pi. Pi is nothing but the searching probability of the ith key. Okay, so searching probability of k1 is nothing but 0.15. Searching probability of p2 k2 is nothing but 0.1 and so on. Okay, so what does it mean searching probability? Suppose if we say searching probability of k1 is 0.15, it means that 50% probabilities or 15% chances are there that we are searching for key K1 out of 100 searches. Okay, so that's what we want, and on that basis or on this statistics, our tree should be optimal. Optimal in the sense that we want to reduce the number of comparisons. Now, another thing is that the unsuccessful search. Suppose if we are searching something which is smaller than K1. So how the basically search is implemented in the binary search tree? In the binary search tree, the search start with the root node. Okay, and we start with the root node. Okay, if the element that we are interested in searching is smaller, then we go in the left side. Otherwise, we will go in the right side. Okay. So similarly, we traverse from the root node to the leaf node, and depending on the comparison. So if D0 is nothing but a set of all values which is smaller than K1, which is smaller than first key or K1. Suppose the value of K1 is 6. Okay. It means that if you are searching for 4, or if you are searching for 5, if you are searching for 3, it means that these particular keys are not at all present in the binary search tree. So D0 is nothing but this range of unsuccessful search. Okay. Now consider this. What is D1? D1 is nothing but all those values which are larger than K0 and smaller than K2. Okay. So these are the values of D1. Like suppose, for example, just consider the value of K1 is equal to 5 and K2 is equal to 10. It means that the value that I am searching for is for in case of unsuccessful search. So it may be greater than 5, like it may be 6, it may be 7, it may be 8, it may be 9. Okay, but not 10. So D1 indicate the range unsuccessful search between K1 and K2. Similarly, D2 indicate another unsuccessful range, then unsuccessful range, then D4, D5 are all are unsuccessful ranges. Okay, and this K1 to K5, these are the keys that is present. Okay. So if I generalize this, then if n keys are present, then total n minus 1 elements are there for which are responsible for unsuccessful searches. So if we see here that 5 elements are present in the binary search tree, then total how many unsuccessful search are there? Total 6 unsuccessful search are there. Now see, the probability are also given for unsuccessful search. Pi is the probability of successful search, and Qi is the probability of unsuccessful search here. So probability of D0 is 0.05, then for D1 0.10, and similarly for D5 this is 0.1. Here we can note that it is starting from 0 and it is starting from 1, because this n keys are present, 5 keys are present, and total 6 successful searches are there. Now this is first option, which can be constructed by considering first 5 keys and 6 unsuccessful search, and this is another option by consider by which can be constructed by considering k keys, sorry, 5 keys and total 6 unsuccessful search. Okay. Now we can compare these two trees. This is first tree, this is another tree. Okay. Now, depending on the probability, I will just start the calculating the cost of the optimal binary search tree, and I will just compare this. So here you can see one table in which I am comparing, or I am computing the cost of this first binary search tree. Now see, first I will write this node. Okay, so these are the node K1, K2, K3, K4, K5. These are the keys. Unsuccessful side D0 to D5. These are the keys. Okay, here I am writing the depth. Depth is starting from 0. So this is 0th depth, then this is 1th depth, then this is 2th depth, and so on. So what is the depth of K1? Depth of K1 is 1. Now I will write the associated probability here. What is the associated probability for K1? 0.15. So this is the 0.15. Here you can also note that this K1 is occurring at second level. So I need to compare one comparison, then another comparison. So just consider one example in which 100 searches are there. In these 100 searches, I am searching K1 15 times. If I am searching K1 15 times, then total how many comparisons are required for finding the K1? For one finding the K1, two comparisons are required. First, I will compare with K2, and then I will come to this particular node. Okay, so two comparison for one search. And how many searches are there? 15 searches are there. So total contribution is 0.30. Okay, so this contribution depend upon the level or the depth of this. Okay, as we can see here, if I am considering K2, okay, so depth is 0. It means that only single comparison is required if I am searching for K2. So if I am the searching probability is 0.10, then it is point contribution is also 0.10. But for example, consider D4. Where is this D4? D4 is this. Total how many levels are there? If I am searching for if it is an unsuccessful search and I land here. Okay, so one comparison, second comparison, third comparison, and fourth comparison. What is the contribution? D1 probability, this D4 probability is 0.04 multiplied by 4. Okay, so it is nothing but zero point 0.2 here. So these are the contribution of all keys plus all unsuccessful search. So total contribution is 2.8. This is nothing but cost of the first binary search tree. Okay, 2.80. If you calculate the cost of the second binary search tree, then you conclude that the cost of the second binary search tree, it means that this tree cost of this particular tree comes out to be 2.75. So 2.75 is better than 2.80. It means that the second tree is far better than the first tree. Second tree is far better than first tree. Now, what is our task? Our task is to construct binary search tree whose cost is minimal with the help of dynamic programming formulation from these data, from the successful search data and unsuccessful search data. So if we consider that 2.75 is the optimal cost, then our aim is to construct this particular tree, okay, from this data. What is this A part? This A is nothing but this tree, and B is nothing but this tree. So A is binary search tree with expected search cost 2.8, and B is nothing but binary search tree with expected search cost 2.75. 2.75 is better. This is also optimal. Now, how can we construct this? First of all, see, you can note that all searching summation of all the probabilities is 1. So summation of successful search probability plus summation of unsuccessful search probability is 1. So if you can just calculate the summation of all these, so it comes out to be 1 only. That's what you can see here. Summation of all the PIs plus summation of all the QIs is 1. Here you can also note that here I is starting from 1 and here I is starting from 0. What is the cost of searching cost in T? Here we can see depth plus 1. Why we are considering depth plus 1? See here, what is the depth of K1 in this particular? This is tree and this is the corresponding calculation. The depth of K1 is, what is the depth of K1? Depth of K1 is 1 because depth is starting from 0. If depth is starting from 0, it means that which level is this? It is a second level. That's why we are considering plus 1 here in this example. So depth is first added with plus 1, is added with 1, and finally it is multiplied with the probability. That is nothing but the contribution. To see once again here, if we are considering this D4, what is the depth? D4 depth, the first depth is 0, then 1, then 2, and then 3. Okay, but it is which level? It is the fourth level. So depth plus 1 will give me 4. And finally, what is the D4 probability? D4 probability is 0.05. So this 0.05 should get multiplied by 4. That's what it is happening here. Depth plus 1 is multiplied by this probability. Okay, now see. This is the cost of entire tree. Now, we have also noted that summation of all the PIs and summation of all the QI is equal to 1. So, if we segregate this, so depth of KI and this is nothing but summation of depth of PI, and this is nothing but summation of depth of DI plus summation of depth of QI. So, summation of PI, which is ranging from 1 to n, and summation of QI, which is ranging from 0 to n. This summation is 0, this summation is 1. So, what we can write? 1 plus this summation 1 plus depth of ki multiplied by pi, and 1 plus depth of di multiplied by ki. Okay, so this is the final cost. Why we are including plus 1? Because we have considered that the depth is starting from 0. If we consider that the depth would be starting from 1, then we would not have added 1 here. Now we will define the characteristic equation EIJ. EIJ is nothing but the minimum cost of the optimal binary search tree by considering the keys from I to J and by considering unsuccessful keys from Di minus 1 to Dj. Okay, here we can note that if we consider from ith key to jth key. Okay, for an example, if the value of I is equal to 2 and if the value of j is equal to 5. Okay, so it means that how many keys are considered? 4 keys are considered: K2, K3, K4, and K5. And how many unsuccessful keys are considered? Unsuccessful keys will be starting from I minus 1, that is from D1, D2, D3, D4, and D5. Okay, now see. So one R will be there, which will be minimizing this particular cost. So this R will be ranging from I to J. And here it is Qi minus 1. Now see what is happening here. If J is equal to I minus 1, then how many keys are considered? keys will be considered from ith key to I minus 1, I minus 1th key. Now we can see here, from if we are considering from ith key to I minus 1th key, then no such key exists. But in case of unsuccessful search, the initial index will be starting from I minus 1. So I minus 1 to I minus 1 single key is considered, and that is nothing but unsuccessful search. And for that unsuccessful search, the probability is nothing but qi minus 1. So this is qi minus 1, and when j is equal to I minus 1. Okay, so we just consider this unsuccessful probability. Okay, if for an example, if we consider E43, what do you mean by E43? E43. So how many keys are considered? So no keys are considered because it is starting from 4 and it is ending with 3. No keys are considered. But in case of unsuccessful side, how many unsuccessful keys will be considered? It will be from 3 to 3. So one key is considered. That is nothing but one unsuccessful probability, and that unsuccessful probability will be denoted by this qi. Qi is the probability. Okay. So if j is equal to I minus 1, then this expression will comes out to be qi minus 1. Otherwise, we will find some r. So e of I r minus 1, and second expression will be r plus 1 to j plus wij is added here. What is wij? Wij is nothing but the probability of involved keys in successful search and involved unsuccessful search probabilities. Okay, so here we can see PL is ranging from I to J. So this is a summation of probability of successful keys, and here it is starting from I minus 1 to J. So it is QL. So these are the unsuccessful search. So Wij is nothing but summation of all the successful and unsuccessful probability in the range I to J in case of successful search, and in the range from I minus 1 to J in case of unsuccessful search. However, this Wij can also be rewritten as Wij minus 1 plus Pj plus plus Qj. Okay. Here, if I am considering the till j minus 1. Okay. So if I include one more object, then one more successful probability and one more unsuccessful probability will get added, and that will be represented with the help of Pj and Qj respectively. Now see how can we compute this. So P, three argument are considered as input. P, what is P? P is nothing but that vector. Which vector? This P. And Q is another vector of unsuccessful probability, that second row, and N is nothing but the number of keys. Now, we will construct three matrices. The first matrix dimension will be N plus 1 cross N. Second matrix W. What is W? W is nothing but summation of probabilities, successful plus unsuccessful. What is E? E is nothing but the optimal cost of the tree. And what is root? Root indicate this value of R, for which this Eij is minimized, okay, in which we will be storing root. So this expression, the dimension of E will be N plus 1 cross N, the dimension of W will be N cross N, and the dimension of this root will be N cross N. Now, first of all, initialization part. First of all, I is ranging from 1 to N plus 1. So I minus 1, and I minus 1, and I minus 1. Okay. So that will be computed. What is the formula for I minus Wij? See, this is the formula for Wij. In Wij, if it is from I to I minus 1, so Pi is not considered. But L is ranging from I minus 1 to I minus 1. Okay, so only one probability, unsuccessful probability is considered here. So Wi minus 1 is nothing but that unsuccessful probability, Qi minus 1, and Ei minus 1, once again, it is nothing but unsuccessful probability of the I minus 1th unsuccessful search. Okay, now just come to this. This is nothing but my E matrix. It is nothing but my W matrix. Okay, here we can note that mm, this is I, and this side it is J. Okay, this side it is I, and this side it is J. So here, what is this? It is 1 0. You see, I is 1 and J is 0. Here I is 2, J is 1. Here I is 3, J is 2. Okay. So what we are computing? We are computing E10, E21, E32, E43, E54, and E65. Okay, that's what we are computing here. This. and it is nothing but this unsuccessful probability that we can also see here. This is 0.05, 0.1, 0.05, 0.05, 0.05, and 0.1. See the unsuccessful probability in this example: 0.05, 0.1, 0.05, 0.05, 0.05, and 0.1. Similarly, my W is also same. Okay. What is W? W is nothing but summation of all the probabilities. Okay. Here we can see that the top W will be 1 only, because this top W indicates the summation of all successful probability plus summation of all unsuccessful probability. Okay, so this should be 1. Then this loop is starting from 1 to n, and then it is starting from 1 to n minus l plus 1. This 1 to n indicate the number of phases. This I indicate the number of subproblem in the phase L. So it completely depends on phase L. Here we can note that this is phase 1, this is phase 2, phase 3, phase 4, and phase 5. Total how many phases are there? 5 phases are there. Okay, so how can we write in terms of this? What is the value of n in this equation? Yeah, in this example, the value of n is 5. So it is ranging from 1 to 5. Okay. Now I is nothing but the number of subproblems. Here we can note that in first phase, 5 subproblems are there. In second phase, 4 subproblems are there. In third phase, 3 subproblems. Fourth phase, 2 subproblems are there. So subproblems are getting reduced. Okay. So it is ranging from 1 to n minus l plus 1. Just an example, if the value of l is equal to 3, then it is n minus l plus 1. So what is this? 5 minus 3 plus 1. So this is 2. So 3 subproblems will be there. Now, depending on this I and L, we need to define J. J is a function of I and L. Here, what is this? It is 1 1. This is 2 2. This is 3 3, 4 4, and 5 5. Then once again, this is 1 2, then 2 3, then 3 4. Okay. So depending on this, we will just decide the J. Now listen, Eij and Wij needs to be computed. So Eij is initialized to infinity, and Wij is nothing but Wij minus 1 that we have already computed in the previous phase. Or if it is the first iteration, then it is initialized and plus Pj plus Qj. Okay. Now what I need to do, I need to just find the value of R. And what is our expression? Our expression is this. Eij is equal to minimum of R such that this expression is, this complete expression should be minimized. Now see, if R is ranging from 0 to J, R is ranging from I to J. So I just compute T. T is equal to I R minus 1 R plus 1 J and Wij. This is the same expression. I R minus 1 R plus 1 J and Wij. Okay. Now Eij is initialized to, infinity. Okay. Then if T is found to be lesser than Eij, then Eij is equal to T. And what is this T? This T is nothing but that R for which it is minimized. And the value of that minimized index is stored in this variable root ij. Similarly, I will be compute this 3 matrices: E matrix, W matrix, and root matrix. So see, this is the final computation of this E matrix, W matrix, and root matrix. Now, how can I get, or how can I construct the tree? Once you have computed this, so you can recheck this once. The top value of the W matrix should be 1. Okay. And from this root matrix, I can reconstruct the tree. How can I construct the tree now? What is the value of 1 5? What is the value of 1 5? So 2. What does it mean? If it is 2, then total how many keys are present with us? Total 5 keys are present, and total unsuccessful 6 unsuccessful keys are present. So successful keys are K1, K2, K3, K4, and K5. And unsuccessful keys are D0, D1, D2, D3, D4, D5. Just check the value of this A1 root 1 5. What is root 1 5? Root 1 5 is 2. It means that second key, that is K2. K2 should be the root of optimal binary search tree. What is optimal binary search tree? This is first figure and second figure. This second figure is nothing but the optimal binary search tree. If K2 is my root, then I need to decide what should be in the left side and what should be in the right side. Okay. What is the relationship between K1, K2, K3, K4, K5? K1 is less than K2, K2 is less than K3, K3 is less than K4, K4 is less than K5. And as it is a binary search tree, left side should be smaller and right side should be larger. Another thing, that successful keys will be at the internal nodes of the tree, and unsuccessful keys will be at the leaf level. Okay, so here you can see these are the unsuccessful keys: D0, D1, D2, D3, D4, D5. All these are leaf nodes. However, K1, K2, K3, K4, K5, these are the internal nodes. Okay, so K2 is my key. If K2 is my root node, then in left side, how many keys are remaining? Only single keys, that is one. And in right side, how many keys will be present? Right side, three keys will be present. So, how many keys are present in right side? Three keys: K3, K4, K5. Now, I am having three keys in the right side: K3, K4, and K5. Among these three keys, K3, K4, K5, I need to decide the root. Okay. If I need to decide the root node of that subtree, which consists of K3, K4, K5, then I will look at the once again that root matrix, and which entry I will check there. I need to check in the root matrix 3, 5. Okay, just go to this root matrix and just check 3, 5. Where is this 3? See, I is this side and J is this side. So this is 3 and this is 5. Okay, if you check here, this is 3, 5. And what is 3, 5? 3, 5 is nothing but this 5. It means that in the right side of that tree, K5 should be root of that particular subtree. Just look at this now. So this is my K5. Okay. If it is my K5, so total how many keys will be there in this subtree? This will be K3, K4, and K5. So K5 is the now. When I come to left of this K5, so two keys are remaining. Which keys? K3 and K4. Now I need to decide at this particular position whether K3 will be there or K4 will be there. So for this, I need to once again check the root matrix, and I need to check which entry 3, 4, because we are having two keys K3 and K4. Just check at that root. This is 3, 4. Okay. So this is my 3 and this is my 4. So if I look at this entry, 3, 4 is nothing but K4. It means that K4 is the root of that particular subtree. So K4 is the root. If K4 is the root, then in the left hand side only K3 will be present. But if you come in the right side of K4, only one unsuccessful probability will be there. That is nothing D4. Similarly, I can just write it D0, D1, D2, D3, and D4. Okay, so this is nothing but the construction of optimal binary search tree. And if you come or if you calculate the contribution of this particular tree, then it will comes out to be 2.75. How it can be computed? Just I'm considering the contribution. Okay, what is the contribution of K2? It is depth 0. The contribution, what is the probability of K2? The probability of K2 is zero point 0.1. So zero point 0.1 is the contribution. What is the contribution of D2? So just check how many levels are there. So first, second, third, fourth, fifth. So total how many levels are there? 5 levels are there. And what is the probability of this unsuccessful search? So 0.05. So 0.05 multiplied by 5 is nothing but 0.25 is nothing but the total probability, total contribution related to D2. And if I sum all these things corresponding to this particular tree, then it will come out to be 2.75. Okay. Now the final thing is that the total time complexity for that algorithm. So here L is ranging from 1 to n minus L plus 1. Here we can note that the outer three for loops are there. First outermost for loop, middle for loop, and innermost for loop. Outer for loop is running n times. Inner for loop, this middle for loop is running also approximately n times, and this is the innermost loop which is running from I to j. And what is the upper limit of I to j? The upper limit of I and j is nothing but n. So more specifically, we can consider that it is also running n times. So three for loops are there. It is running n times. So the time complexity will be n cube. Okay. The final time complexity of this will be n cube. So this was the optimal binary search tree. Thank you.